So good morning, everybody. Very nice to be here. Welcome, yes. Welcome to all of you who are coming from out of town, and those of you also local, some of the local people. Very nice to have you in Albuquerque at UNM. So on behalf of the IEEE Communication Society Education Board, I would like to welcome you all to the third ComSoc summer school. The last two, in 15 and 16, were held in Italy, in Trento. I was privileged to be there as a speaker myself a year ago. Well, actually, a bit more. It was in June. But this year we tried to, match that how well the event went in Italy the last 2 years, and show off a little bit of New Mexico. I'm also new here myself. I only joined here a year ago. But I hope that you enjoy the next few days. We have excellent speakers. The ones I call the main speakers, there's 4 people who will do like the main program during the day, roughly from 9 to 5 every day, and 9 to 4. And in the middle of the day, we will have lunch at 12. And then typically after lunch, starting tomorrow, we will have those hands-on demo sessions. Today, after lunch, we will have a presentation. Where's Camila? So we will have presentations essentially every day right after lunch. There will be one of your colleagues who has been delayed due to flight delays last night will present on behalf of IEEE Young Professional Program, and then we will have a short presentation on behalf of UNM Global Programs, and Camila Agui will present on IoT and smart transportation. We will have tomorrow the hands-on demo with the smartphones from Professor Stachos from Guelph, and then Wednesday Rich Bowley from National Instruments is here to do a hands-on with software-defined radio, I think. He's not here yet, but he's arriving today. And then on Thursday we have a talk from Yannis Papapanagiotou, one of my former PhD students now at Netflix, who will present about cloud, right? So this is like the middle of the day program, and then the 4 speakers, starting today with Professor Scaglione from Arizona State, and then tomorrow with Fabrizio Granelli and so forth. We will have the main speakers holding the main program from 9 to 4, 9 to 5. Okay. Don't forget today at 4 or 4-ish, or right after 4, we will make our way to Hodgson Hall for the opening reception as well. So we hope to see you all there, and I'll try to get some of my colleagues and the dean and some other people from the university to be there as well. What else? Logistics, you're in very good hands. From the global office, they've done so very well for you so far. Megan, thank you so much for doing this, and Gemma today for holding the door. What else? Any other immediate reactions or questions or concerns? Good. Well, then, without further ado, I will present to you our first distinguished speaker who is going to do the main program today. Professor Scaglione from Arizona State University is here today to present to us on communications for large-scale cyber-physical systems. We're very, very excited to have her here. She has been here before, which was a surprise to me. I had no idea. Yes. But it's very nice to have her. We have crossed paths before in these areas of cyber-physical systems and smart grid communications and such general areas of common interest. So we're very, very delighted to have you here. Thank you so much for being here. The floor is yours, yeah?
Thank you.
Thank you so much.
Thank you. So this was my first job was at the University of New Mexico. I was here from 2000 to 2001. This was the very first assistant professor job. So let me start with a little bit of light content. So the IoT is such a wide area that what we are trying to do is not to overshoot, right? So typically, at the undergraduate level, you try to learn everything. At the master level, you go a little bit more in depth. And then you eventually learn a lot about a single area. But the risk is overshooting. And I would say that oftentimes when we talk about IoT, it's such a wide area full of references to applications. So we are going to try today to not do that. And I will start with a little bit of history to motivate why we are here talking about Internet of Things and what has changed. And this is old stuff. It's nice to see once in a while black and white pictures. Does everybody recognize that guy? That's von Neumann. And I think everybody recognizes this guy, Shannon, right? So this is a very long time ago at this point. So what did they come up with? They came up with a general concept, the concept that everything could be represented digitally, just utilizing two values or two states, ones and zeros. And von Neumann was responsible for a general architecture for computing machines. And Shannon essentially helped us understand that every kind of information could be represented also digitally. And this was particularly apropos because almost concurrently, people more in the hardware side had discovered how to make very simple chip that could hold the state 1 and 0 and could be used to amplify signals also with very small devices. And so the rest is history. Then that's what came out of it. This large communication infrastructure, the internet. You grew up with it. You didn't know this, but I didn't grow up with it. This came out, and it was very exciting. That's why I'm an electrical engineer. It was very exciting when this started working. And then, fast forward, we have a lot of cat photos that you can see on these. But obviously, we have a lot of important applications. And the challenge in teaching about and learning about these new applications is that there are several excellent textbooks now that clarify a lot about this basic theory. But unfortunately, so you are not incentivized to write another textbook necessarily because the basics are the same, right? But the examples in a lot of these textbooks are ancient. And I would say that in the field of digital communication, a lot of ancient examples exist. And even in wireless communications, many people are focused more on the cellular side of things and wrote excellent textbooks about wireless, but people are not that motivated to write a textbook about the Internet of Things and all that is coming with it, because the basics are there, right? It's just that the examples are not. And if you are hardcore communication engineers, maybe you don't know that the Internet of Things has a grandparent as well. And in fact, the electric power industry is the one that made a formal model for this, because they didn't have the ability to control an infrastructure that was growing enormously in size. So they couldn't just make analog circuits. They realized that they needed communication and they needed to control remote location systems. And so there is this field of industrial automation that attracts some computer engineers, a lot of control engineers, and these are not necessarily, or were not necessarily expert, just like people that work in robotics. They were not necessarily expert in communications or in computer infrastructure, except the computer engineers, I would say. But they were expert on the physical processes that they were trying to support through these networks. So the notion of connecting machines is not a new exciting thing. It has been done for a while. And this happened about mid-60s, mid-70s. These concepts were formalized, and the reference model that was used, you will see this word. I won't use it very much, but it's called SCADA, right? Sensory control and data acquisition. It's simply a formal model that says that you have to gather information from sensors, and you have to be able to send control signals to actuators. And it's a hierarchical infrastructure that says you have two levels of aggregation, and eventually everything goes into a central control station that has the full control and the ability to essentially make the system operate in a safe fashion. And a lot of the controls are local, and some of the controls are upstream. And the reason why a lot of the controls are local and some are upstream is really latency of this communication infrastructure. And a lot of them in the ancient time referred to this as telemetry, right? So they couldn't see the system state in real time. They could only see it with a certain lag, right? So they really had to make big decisions, and central operations, looking in the rear view mirror, what was happening in the system. And flash forward, what is happening really is that industrial control is getting personal. So that's really the difference between the IoT and this old style industrial control, right? Where we have embedded computers, these von Neumann machines, all over the place in every single device that is an electronic device pretty much. And then these are becoming responsive and they need to communicate. That's really what makes it special. And we're not stopping there, actually. The future is ripe for change. In part is due to the fact that finally the people working on robotics are finally getting it. And it's also a result of Moore's law that has allowed much more powerful computers to be employed in these applications. So you will see that the service industry, not just manufacturing plants, are going to be invaded by robots. They are coming. Self-driving cars are definitely coming. And I don't know if Domino will deliver pizzas with drones. There are a lot of issues with that. But at least the technology in principle is there. So we need to provide, as communication engineers, networks that are reliable, that will allow these applications to thrive. And so all of this is starting to form an ecosystem, and that's really what makes it complicated, because it's invested, the people are invested in so many different areas, and we want to design an infrastructure that will support all of these areas. Is that even possible? The data requirements, the type of controls that are applied in these different areas are very different. And so we hope always that the domain expert will come up with some requirements, right? That we communication engineers do not have to understand anything. But if there is something that Shannon has taught us, is that you have to understand what is the source you are trying to encode and what is the purpose of that information, because only then you can actually optimize the network itself. It doesn't only matter the pipe you build, right? It does matter what representation you actually need to do what you want to do. What is the end of your communication matters as much as what is the source of your communication in this context. And are we happy about that? As engineers, we are really extremely happy, because everything will have a solution, will be easier and more efficient. There are a lot of social consequences that we have to be aware of. So this group is probably not going to be unemployed, but if automation invades also the service industry, there is going to be a lot of unemployed and unhappy people, right? So there are social issues that I want to make you aware of. And maybe because of that, you know, I don't know, there are a lot of reasons why I focused on the energy application, but one of the reasons in part is that solves another big problem, which is climate change, that I believe exists. But there are a lot of social issues in other applications like the ones that I mentioned here, right? You will not need drivers anymore, you will not need delivery people, and right now these are the type of jobs that exist because a lot of the retail is moving on the internet. So there are a lot of consequences that we need to be aware as citizens. On the other hand, as I said, you have plenty of opportunities. Like, the world is an oyster right now. This is a set of companies that occupy the various areas where IoT professionals can make a living from. And I would say that right now the idea of data analytics is the one that is in everybody's mind. But there are a lot of problems to solve underneath, right? We have to develop a very good, responsive, energy efficient devices with capabilities of pre-processing the data that come, right? Because if we ship all the data in the cloud, in big server farms, that obviously doesn't sound very efficient, given that we may have a lot of computational power at the edge of this network. And obviously, we need to create a very resilient, very reliable backhaul to supply this ability to get the information where they have to go. And in this image, definitely right now, the information is getting onto the cloud. And here it's even a more impressive diagram that shows that as of 2014, this is a list of 600 companies that occupy this space. Okay, so there are a lot of new applications, and wireless connectivity is preferred because a lot of these objects are mobile or because it's easy to deploy. But as I said, we rarely motivate our teaching of the basics with these particular applications. So we want to understand what protocols and what data, what are the middle aspects of it. And so it's good to right now make a snapshot of what are the prevalent applications. Maybe there will be other applications in the future. As I said, transportation and logistics is one. I didn't mention the application that will be the focus of this course, power systems. There are a lot of other applications though, smart city, smart building automation, wearable, that's very hot. Process monitoring and control, this will be the revamped industrial control system applications. And then environmental monitoring as well as intelligent agriculture, because apparently people don't want to live in the country, so you have to automate that, right? So now I want to say that this is a very varied landscape. It's not true that you want the same infrastructure for all of these applications. Another reason why I chose the utilities is you could say that's a kind of industrial control, but that's a very challenging application because it's very wide area. You are transporting a commodity that moves at the speed of light, electricity, and you have serious concerns about safety. So this has to be extremely reliable. There are other applications for which I would say the challenge is slightly smaller, right? This truly has some amount of challenge because you have to just project a virtual reality world. If you are exploiting the cloud, you do have to have a method to overcome the latency of going back and forth from the cloud. The smart home application, if you have to turn on the light or the air conditioner remotely, this is not a big deal, I would say. It's not that complicated. The wearable could be complicated if you start to put a lot of sensors on the body. They are in high proximity. You cannot make them bulky and big. So there is not a lot of local processing that you can do. If they are in body, you have to, inside the body, something you can swallow or have in your body, there is serious electromagnetic propagation attenuation that you have to fight. But again, once again, these are not extremely demanding. You have to cover a relatively short distance and you do not have enormous amount of data. The real problem there is the scaling of the computation and the circuitry and the energy. But as I said, if you look at large-scale infrastructure IoT, then you have these pictures where there is this magic communication network that connects everything, and you literally have to connect systems that are of the size of entire countries, right? So the US grid is divided in three different infrastructure that have to operate with tight coordination. And believe it or not, right now the model is this, that there is a central control over certain wide areas, and that central control brings a feedback control signal or operation settings to different actuators. And then the physical world is completely coupled. That's why you need a central control and sensors to refresh the state of the system so the intelligence can take an action. Okay? So I divided this presentation in essentially 4 parts, of which I will say I'm not sure I will reach. The last part is really sort of a nugget to alert you to another aspect that is very much in our mind, hacking of the IoT. But I will start from pure communications and giving you sensor networking fundamentals. Then I will talk a little bit about decentralized processing and what does that mean, right? So that is, some people refer to it as the fog. Instead of bringing stuff in the cloud, in some server farm, you actually do communication, you computation locally, but it's not entirely locally because you actually do exchange information with peer devices in the network. And then I will talk about the application of smart energy, not from the point of view of the Zigbee devices necessarily, but really from the infrastructure point of view, so that you will understand what are the real challenges in managing this infrastructure and how can the smart energy IoT help the infrastructure evolve. And that will be in the afternoon. So let me start with sensor networking. And I know at 10 we have a break, so I will have to break in the middle of this. So what I'm going to describe is still a little bit old. It's about 15 years ago material. Some of it is even older. And why do I want to explain to you this? Because, you know, around 2000 and 2001, when I came here with my first job as assistant professor, the really exciting thing were cell phones, right? Mobility. The fact that you could essentially carry this device that then later on became apparent could be your personal assistant. But at the time, the main idea was to have a device with which you could transmit voice, of course, but also do email maybe, right? Connect to the internet. So wireless network design, at least at the time, was divided in basically two different classes. The computer engineers were still interested in embedded system, right? So they wanted actually to make different communication device connect that were not necessarily cell phones, they were computers. And so they were interested in computer networks and embedded device networks. And a lot of the communication engineers were actually focusing on cellular. And from that, from the limitations of first and second generation cellular systems, people came up with a lot of networking concepts. But then they realized that they could help the networking engineer use wireless much more intelligently, exploiting all the lessons that they were essentially learning by trying to make wireless communication very efficient for these much more demanding applications that they were looking at. And basically also they were responding to some negative results that were obtained about how effective would have been the communication over wide area in terms of power and rate for networks that were interconnected from peer to peer. And now mesh networks are a reality. You have them all over the place. But this was an interesting lesson that made people understand how much you could scale that concept, just analyzing how these could scale. And the advances in cellular networks led to a bunch of schemes that unfortunately I don't think have impacted the IoT, at least not yet. But they're still impacting a lot the cellular network generations. And as you will see, you know, the real challenge right now is to utilize some of the concept in the new standards for cellular communication to support some of the applications that were sensor network applications. So let me start with the starting point because this clarifies to a certain extent how all these notions that came about to fix the scaling, the poor scaling of mesh network came about, right? So the starting point is the cellular network were a network that had to support voice application, but soon enough they became systems that were supporting IP and packet transmission. And if you start making this network denser and denser, you have to come up with more and more sophisticated techniques to support that. So in both networks, the real problem is interference management and complexity. But in the cellular network, you have a high deployment cost because what you're trying to do is just the last edge of the network. You still have to have a wide network as a backhaul. While in mesh network, what you wanted is simplicity. You wanted to deploy sensors and have them communicate. And obviously, all of these systems had to coexist originally with a very strict subdivision of the spectrum between services. But then people realized that by making the spectrum unlicensed, they could unleash all the applications that now we talk about, like IoT, content delivery through personal devices and so on, that is supported by Wi-Fi. And the real issue came about of essentially not being affected by the tragedy of the commons. This spurred a lot of innovation because we wanted to essentially contain the effect of interference between competing technologies and within a certain technology. So the first big leap that was done in cellular communication that was sort of a defining moment. A lot of people thought there was spread spectrum and CDMA, right, at the time when I was graduating. But in reality, it wasn't. What really changed things was the understanding of multiple antenna diversity and how to encode for broadband communications. This was called pre-coding. These are areas that I was working on early on at the beginning of this century. And the great discovery here was that you could increase, by increasing antennas, you could increase the capacity n-fold, where n was the minimum between the number of transmit and receive antennas, right? So you were not paying for most bandwidth, you had the same exact amount of bandwidth, but if you put more hardware, you could increase your rate. And you could increase it linearly, right? And so n is effectively the rank of this linear operator that represents what happens both in space and time, right? And the idea was that you can still use your old time modulations, BPSK, QPSK, and so on and so forth. But instead of looking at these symbols as something that you have to transmit directly on the channel, what you can do is you can reshape them to fit like a glove this particular distortion that the channel is causing. And what is this distortion? Well, if you transmit in a broadband fashion, you are affected essentially by inter-symbol interference, right? This is well known, okay? And people were really killing themselves trying to equalize this channel, make it as flat as possible, until they realized that instead of equalizing this channel, what they had to do is to essentially exploit the selectivity of the channel by transmitting essentially a lot of narrowband signals, each of them designed through a digital precoder. So now if you have a narrowband signal, what you have is that this operator is just representing the fading of each pair of transmit and receive antenna and is mixing the input to your channel, and then you have your usual noise signal. If you have a broadband communication, instead you have this block convolution, right? So each of the links between every transmit and receive antenna becomes a fading channel, right? And you can actually represent this particular relationship, right, that I wrote in this block fashion, blocking this even further, taking a bunch of blocks that you transmit over time, right, and defining a block matrix, right, where the k and block will contain this object. And so now you can write a space-time operator H, linear operator H, and the precoder F is just taking care both of what you observe in time and what is happening in space. And as long as this is not this object operates exactly as a convolution, which will mean some stationarity between these links. They have to be, at least in the block that you are transmitting, linear time invariant. Actually, there is a general structure for the precoder that you want to utilize to essentially shape your system in time, and that would be provided by using multi-carrier transmission or orthogonal frequency division multiplexing. Okay? But you are not done. The rest of the job is essentially taking care of all the responses that you have in each sub-frequency that characterize the multiple inputs and multiple outputs. And the general structure of the precoder that you want to utilize, if you have knowledge of these frequency response at the transmitter, is to essentially split this channel in a bunch of parallel subchannels by using a singular value decomposition. And that's optimum, capacity optimum. It's the best thing to do. Okay? It's always like this. And we understood this early on. What if you don't have the channel state information? Then in this case, what you have to try to do is to exploit time and space differently. So you have to build codes that embed the symbols in such a way that it is possible at the receiver to obtain a similar effect, that you can recover each one of them through an operator that now you have to estimate. But the operator H that you observe through this mapping is going to be much more benign. And these type of codes were originally invented considering a multiple transmit antennas but a single receive antennas. You can generalize the concept, obviously, to multiple receivers. And so the way it worked is that you had a set of fading coefficients from the multiple transmit antennas to the multiple receive antenna. That would be the vector S. And all your symbols were encoded in this mapping. There was a matrix that mapped symbols in space and time. And initially, the code design performance that was targeted is to achieve greater diversity, right? And what you try to do, or you strive for, was to transmit as many symbols as possible during the block of time that you had to occupy the channel, which is, in essence, the number of columns of this matrix G. You wanted to transmit as many symbols, as many columns you had in G, while at the same time you needed to satisfy certain basic conditions. That for every different vector of symbol that you were transmitting, you were getting a matrix difference that had a non-zero determinant. And also that for every single symbol set, the matrix itself had full rank. Okay? And the diversity is defined as the log of the probability of error over log SNR. Yes? No, I didn't define capacity in any of these, right? Oh, I said that the capacity grows order of n, like the minimum between the transmit and receive antennas. This is the gain of MIMO, and that's the gain that you obtain if you have channel state information, right? And what happens is essentially that the number of these subchannels is exactly n, right? So each of that carries a log n plus SNR capacity, right? And you have n of them, so you can have that gain of n. Thank you for the question. Okay? So space-time coding can achieve also similar capacity gain. In this case, I have only one receive antenna, so I cannot achieve a capacity gain of n, but I can achieve a capacity gain of log n. Okay? But in this case, people were actually also concerned, as I said, about this diversity that I get, right? And the fact that the slope of the probability of error was improving essentially with the rank of this matrix, this space-time code matrix. Okay? So this was completely divorced from the notion of mesh network. In mesh network, people were not really thinking about MIMO or how to increase the capacity of the single link, because their main concern was to actually have all these links, whatever they were, coexist. Okay, so they utilized actually a much simpler abstraction. In most cases, they didn't look closely at the physical layer. They were trying to have a fairly robust physical layer, but they were more interested in multiple access and providing end-to-end connectivity through routing, right? Until I would say this seminal paper by Gupta and Kumar that started saying, okay, but let me forget about finding another algorithm that maybe gains something in terms of access. Let me try to measure in a very abstract way, even if I do not have any particular routing algorithm in mind or access algorithm in mind. Let me say what I can support just based on an interference argument. Okay? All right, so in cellular networks, originally people were thinking about completely saturated information, for which maybe a circuit switched model applied best. Also originally the packet switching was really the domain of this particular mesh network. So he came up with a way of bounding essentially how much you could transmit over a network. What would be the maximum rate you can transmit per unit area? So he defined a different concept, which was the transport capacity. And he said, suppose you have a bandwidth W, right? Now you don't have antennas, who cares, right? So you can transmit at most at a rate W, right? I'm not going to be concerned about how many bits, this is your baud rate, okay? And then eventually I can have a log 1 plus SNR, it's a constant, has nothing to do with how many of these I can transport, okay? And I want to understand how many I can support simultaneously. They have a certain distance. So given a certain distance Dij and a node transmitting at rate W, my figure of merit is going to be the following. It's going to be W times the supremum of the sum of the nodes' distances that are transmitting simultaneously, right? So these are the links that are active at the same time, and so these are the bits that are flowing in that time instant or in that time slot over the network, okay? And so he came up with what I would say is the typical way of looking at the collision channel, right? So he called it the protocol model. He says that, let's say that I have two pairs, the pair of transmitter-receiver Ij and the pair of transmitter-receiver Kl that are different, and they both belong to the set that are transmitting at the same time. So the condition is that the distance between the transmitter K and the receiver J, right, has to be greater than the distance between transmitter I and transmitter J by a gap, right, delta, after which the interference, we can say, is sort of 0, okay? So that was the percentage that you were paying for having these two coexist. He also said, you know, let me focus on this protocol model, it's much easier. My argument becomes essentially geometrical, but I understand that the physics doesn't go that way, right? So I actually could account for the interference and look at a model which is closer to duality, where I am trying to put a constraint on the signal to noise plus interference ratio. And so I am requesting that the interference, which is caused by all the simultaneously transmitting nodes that are not node I, right, plus the noise n, should be smaller by a factor beta than the power that is transmitted by node Pi times a path loss, which he modeled as a simple deterministic path loss, Dij minus alpha, and alpha is this propagation constant. So he understood that through the protocol model that basically what happens is that you have certain area which is forbidden from transmission. That's what you're losing, Okay, so that's what prevents you from everybody merrily transmit that is available and in proximity of a receiver. And he also showed that the best thing is to always transmit a single hop to your closest neighbor, right? So you couldn't actually go faster. You couldn't transmit a greater transport capacity if you were trying to reach somebody who was further away. You lost the minimum amount of area if you were transmitting at the lowest power possible to keep you connected, okay? And in fact, that caused a frenzy of studies on random geometric graphs, which are exactly these graphs that have a connectivity which is based on having somebody within a certain radius. Okay, so he discovered that there is an exclusion region, and he essentially, with a geometric argument, understood that the exclusion region, due to the fact that node I is transmitting to node J, goes like pi over 4 delta, which is that percentage that we put in the protocol model, right? Times dij divided by 2 squared. Okay? So that's this kind of circle, right? It's a lower bound. It's not the exact area. So by using this lower bound, he was able to bound the transport capacity in essence. And actually, he found two bounds. So that's why it's called the theta of square root of n. He found that you could achieve that bound tightly with a lot of coordination. Yes? In this case, this is SNR. So it could be Gaussian or not Gaussian. It's just that you are assuming that your figure of merit is the SNR. This is Euclidean distance. Okay? And this is, you can argue that this is not a very realistic path loss model, but it's very much used, especially if you are in close proximity, but it's very much used to make calculations, sort of, you have to be at a certain distance from the antenna, etc., etc. So this will not hold in extreme proximity, but let's say you are 100 meters away from this transmission antenna, is not transmitting very far. On average, is not a completely unreasonable approximation. Okay? And if everything was Gaussian, it would be optimum. This would be SNR, and your rate would be log 1 plus SNR, so you want to transmit at least this number of bits. Okay? All right, so by proving that the transport capacity scales like the square root of the number of nodes, right, that are in the entire network, in his example, the entire network occupied a region which was a unit area, unspecified. So these distances were all less than 1, but 1 could have been kilometers, obviously. Then what he argued is that the transport capacity, if you normalize it by the number of nodes that are present, actually vanishes, right? Because you cannot grow higher than square root of n. If you have n nodes, right, it goes down to 0, like 1 over square root of n. And this was the proof, essentially. So he just showed that the sum of the exclusion regions is greater than that bound that I gave before, and is obviously less than the area. But more importantly, he also found another upper bound here, right, for the sum of the distances themselves, which showed essentially that you also have a square root of n scaling for the upper bound, and the lower bound for a perfectly regular deployment you actually can achieve. So basically, he showed that in essence, this bound was valid. That's why it's called the theta of square root of n. So then people started to wake up and said, wow, we are discovering this MIMO trick. Can we use MIMO, right, in this context? And in this case, they were making a little bit more benign assumptions, right? So in the case of space-time coding, I told you, you do not have channel state information. And in that case, I'm trying to support a link from a multi-antenna transmitter to a multi-antenna or single antenna receiver. But let's say that I have a multi-antenna transmitter, I can also use it to transmit simultaneously to multiple nodes if I actually know the channel state at the transmitter. And what I can use is another form of MIMO. What MIMO will do in that case, if you have only one receiver but multiple transmitters, would suggest that you have to beamform to each of them, okay? So this will be an orthogonal channel to this receiver, an orthogonal channel to that receiver, an orthogonal channel to the other receiver. And what happens is that each of these channels has a complete zero at these different points. Obviously, it's a little bit complicated because you will have to know the channel at the transmitter, but this actually was known much before MIMO. This is called beamforming. And you can form this beam and support multiple transmission. So from the point of view of the protocol model, that meant that in this region you can actually support multiple non-interfering communications if you had multiple antennas. So people studied this. About 3 years later, there was an article that showed that tough luck, unless you put infinite order of n transmit antennas, is not going to buy you much, right? So you still will have a vanishing rate. You just can increase that, increase the transport capacity by square root of the number of transmitters. It's kind of intuitive, but I wanted to report the fact that just applying the MIMO kind of trick to the single transmitter was not going to cut it, okay? To the single link was not going to cut it. So also we want to consider another aspect. In the original model, the transport capacity was the objective, and so the authors of that paper were trying to maximize the transport capacity irrespective of latency. Now, if you make cells very small and you have to transmit multi-hop, obviously the latency increases. And so later on people observed, okay, well, but if latency is really your concern, then you should have a TDMA scheme, right? So you should try to blast your power to reach the end of the network as soon as possible. And in this case, obviously, the transport capacity is much worse because it's order of 1, it's a constant, and so it vanishes like 1 over n, and not like 1 over square root of n. So it vanishes faster. But later on, people were trying to look at this trade-off between the transport capacity and the latency for a certain given number of nodes in the network to understand in the limit how this ratio will go. And people proved that both TDMA and the protocol model that Gupta and Kumar had studied, they were not very complicated. They had a ratio between delay and transport capacity which was 1. Okay? So TDMA has much better latency, so can we do anything different? Okay? So there was another approach to just improve the transport capacity that was used, which was called having opportunistic gain. Right? This was inspired by another result that was obtained in the context of cellular communication that suggested that if instead of focusing on the single link, you have a multiple access channel, one thing that you can do when you schedule your transmission is instead of having all of these transmit simultaneously and try to decode them simultaneously, what you do is you pick the node that has the highest SNR and have that node transmit. And the argument was, well, if now these networks are packet switched, if you do that, you will have the maximum stable throughput. That means that you will empty the fastest you can the queue of this node, right? And then, so that will transmit through the maximum number of bits. And then if these coefficients are random, then eventually everybody will have a shot at doing that. In the context of multi-hop networks, obviously you were not looking at a single base station, but you were looking at different nodes. So the argument that was made was, well, suppose that the nodes are mobile, right? So if the nodes are mobile, they eventually will come close to another node, right? So they will have an excellent channel towards a certain other node. So if they could afford even more latency, right, and wait until they move in the proximity of that site, then what will happen is that you could actually have a much better transport capacity. And that led to another concept, which was the concept of delay-tolerant networking, right? And led to a calculation of the transport capacity that happily was giving a theta of n, and therefore it was scaling properly, it was greater than 0. Now, obviously, it wasn't for free, right? Because mobility costs you a lot, right? So if you really are relying on these to transmit IoT stuff, tough luck, right? This would not be an appropriate solution. So other people started thinking about a different concept. All of these nodes are antennas. Can they somehow cooperate? Can they distribute the benefits of MIMO if they cooperate in transmitting information? One of the nice things about wireless channel and the bad things about wireless channel, it's a broadcast medium, right? So can you use the fact that people can overhear these communications instead as being a foe, as a friend? Because you actually have multiple transmitters that have the same information. So if you can cooperate, you can realize this benefit without additional hardware. And eventually, you will have, order of n transmit antennas, right? If you gain a bigger and bigger portion of this. And so the notion that nodes have observed or can observe correlated information also was getting popular in the wired networking context. And there was a famous paper by Young that proved that instead of switching information in a wired network, you could use network coding to multicast more efficiently data. So these two concepts were sort of becoming popular in parallel. So what is a cooperative link? Is just exactly what I said. It's trying to extend the notion of MIMO links to a setup where you have separate devices, and these devices have the same information to encode, and they are trying to send it to a bunch of receivers that overhear a single copy, and then potentially they can locally exchange information to decode jointly, right? So if they did that, they will have an order of n, right? If I have 4 here, 4 transmit antenna, 4 receive antennas, then I have an order of n gain. And so that led to the concept much later, after 7 years, right? Of what could we do without putting wheels on these nodes to change the equation of the transport capacity. We could utilize what was called a hierarchical form of cooperation, where essentially nodes are overhearing or by essentially interacting, they were transmitting a unison and decoding a unison, and they were doing it in a hierarchical fashion. They were doing it for bigger and bigger ranges, and so this was called hierarchical cooperation, and obviously it requires a nightmare of coordination, but it was done in different phases, right? And what the hierarchical levels brought you is that one could prove that the transport capacity for a certain number of hierarchies h was going as a theta of n over a, to the h divided by h plus 1. Okay? So this was recovering the results of previous authors even without cooperation, right, for h small, but if you started to increase h, you had a better deal. Okay? And so these authors also looked at the delay versus transport capacity trade-off, and they realized that there are other forms of hierarchical cooperation that actually can do slightly better, though at the expenses of transport capacity, if you look at the delay as well. Okay? So what I want to do is, but I will say this is a slightly different topic, which is opportunistic cooperative co-design. I would like to break right now because there is a break at 10, and then we resume with this part because it's better not to interrupt in the middle.